Okay, hi everybody. Welcome to the February meeting of the Boston chapter of Citizens Climate Lobby. Tonight, we're pleased to have Dr. Howard Herzog to speak with us about carbon dioxide capture and storage. Dr. Herzog is a senior research engineer in the MIT Energy Initiative, where he works on sponsored research involving energy and the environment, with an emphasis on greenhouse gas mitigation technologies. He received his undergraduate and graduate education in chemical engineering at MIT. He was a coordinating lead author for the IPCC special report on carbon dioxide capture, and in 2018, he authored a book entitled Carbon Capture for the MIT Press Essential Knowledge Series. Welcome, Dr. Herzog, and the floor is yours.
Okay, thank you. It's a pleasure to be here. I'm going to share my screen. I have a few slides, maybe talk for about 10 minutes, and then we'll open it up for questions and discussion. So just, all right. See if I can, there we go. Okay, so I'm going to talk about carbon dioxide capture and storage. And as Gary said, I wrote a book that if you're interested in more information, this is actually a good book. It's aimed at the non-expert and sort of covers the whole field. The chapters are on the right here for the book. So I'm going to talk, when people say carbon capture and storage these days, it's been expanded from what it was in the past. When I first started doing this maybe 30 years ago, it was mainly capturing from large point sources like power plants, mainly power plants, mainly coal plants at that point, and then taking the CO2 that you capture and storing it in deep geologic formations. Now people are talking about capturing, they sort of overlap with what's called carbon dioxide removal, where they're talking about capturing it from the atmosphere. And there is an overlap, and I'll talk a little about that later on, but I'm going to start talking about the original carbon capture and storage first. So a couple quick questions that people ask all the time. First, is this feasible? And the question is yes, that all major components of the system are commercially available today. This means capture. We're capturing today at power plants. We're doing it in industrial facilities. And there are even some air capture plants going on out there today. Then you transport it. It's mainly by pipeline, but there are people working on ship transport, especially in the North Sea in Europe. And also the Japanese are very interested in ship transport, a little more expensive than pipeline transport. And then finally, the storage system, mainly putting it in deep formations under the earth. Those can be depleted oil and gas reservoirs, but they also can be these deep saline formations. These formations, to keep CO2 in a liquid-like state, need to be below 800 meters, basically 2,500 feet deep. So if they all exist today, why is it limited? And the answer is pretty simple. It's always going to be cheaper to emit to the atmosphere than to store it, capture and store it. So opportunities to do this today are going to be in niche areas until more wider carbon policies are put in place. So what are the trends going on with CCS? There was when I started doing this, and I did my first work in 1989, and there was for about 20 years, there was a continuing growth, and that peaked in 2010. And then the interest fell off fairly significantly for the next half dozen years, partly because the momentum for climate policy fell apart both here in the US and internationally. The last few years, it's been picking up, and we see a renewed momentum of this going on. But the interest is no longer focused on the power sector. What's happened over the past 30 years, of course, we see that in the Western Europe and in the United States, coal-fired power is being reduced greatly in capacity. And so India and China is still have that big thing in the power sector. How that will play out, whether they follow what happens here in the West or whether they put capture and storage on those facilities is yet to be determined. But in the West here, the interest has shifted to first industry. Why industry? Things like cement and iron and steel, which together make up over 10% of the world's CO2 emissions, are very difficult to mitigate. Partly because only about half those emissions come from energy use. The other half come from the process itself, whether from the coke used in reducing the iron ore or in the calcining of the calcium carbonate. Those drive off CO2 molecules in addition to what comes from the burning of the fuels. And CCS is sort of a natural there for industry, and there's a lot of interest now being taken up. There is an iron and steel plant in Abu Dhabi that's capturing the CO2, and in Norway, a project has started to do it on a cement plant. Hydrogen's another area. A lot of interest in hydrogen lately. People look at you want to decarbonize electricity and then try to electrify as much as you can, but everything can't be electrified. Hydrogen's another energy carrier. And the cheapest way to make hydrogen today is from steam methane reforming. And so you're using natural gas to do that. The cost here in the United States of that is about 1/4 the cost of making what they call green hydrogen from electrolysis of water. And you can capture the CO2 from steam methane reforming. Is being done a couple places, one up in Canada, one down in Texas today. And the cost of that is still half the cost of what green hydrogen would be. So you can get low cost hydrogen using carbon capture and storage, and that's been termed blue hydrogen. Then, as I said, negative emissions, ever since the publication of the IPCC's report on the 1.5 degree stabilization target, people realized, well, we're going to need negative emissions, even just to get to net zero. And people sort of want to go to net negative. I say, well, it's going to take us, it's hard enough getting to net zero. You can't get to net negative without getting to net zero first. So let's just worry about getting to net zero. And then several decades in the future, when we get there, if we get there, you can argue about whether you want to go net negative. But two of the biggest ones, technologies to do this. The one that are in a lot of the models with bioenergy with CCS. This is basically like a coal-fired power plant, except burning biomass. And what it does is the trees take the CO2 out of the atmosphere. Then you harvest the trees, or you can do it in also vegetation. It doesn't have to be woody biomass, it could be herbaceous biomass, and you take it and you burn it in a power plant, capture the CO2 and put the CO2 in the ground. So the net effect is taking the CO2 out of the air, putting it in the ground. And when you look at the economics of this, it's really the negative emissions, the price you get paid for the negative emissions that drives it. And the electricity you produce is simply a byproduct. And finally, direct air capture is getting a lot of talk lately, where you actually have, like today, we have machines you put on a smokestack to capture the CO2. You can do the same thing for air. Problem is the concentration of CO2 in the air is about a few hundred times less than it is in a smokestack. Therefore, it's much more expensive and much more tricky to do, but there are a few companies doing this. Cost of that, you can actually go on the internet and buy negative emissions through the direct air capture. It will cost you $1,100 per ton of CO2. Pretty hefty price tag on that today. Prices can come down, but there's some things that make it difficult. So it's always going to be in the hundreds of dollars per ton of CO2 for that. That could still be cheaper than, say, if you want to offset emissions from an airplane, where emissions from the airplane can cost you hundreds to even thousands of dollars to mitigate. So that's the field, and these negative emissions are a lot of times go by the term carbon dioxide removal. And there's other negative emissions technologies that don't use CCS, whether it's sequestration in soils or in forests, and they're talking about mineralization type of activities. So if we're going to get CCS from where we are today, and today we're capturing and storing on the order of tens of millions of tons of CO2 from around the world, but we really need to get to the billions of ton level. We have 40 billion tons of greenhouse gases going in the atmosphere every year. If you don't work on the billion-ton level, you're not really going to make a big dent. And so we need to get up a couple orders of magnitude. Well, what will allow us to do it? Well, first, the most important is the creation of markets. That has to be done through policy, whether it's carbon pricing, whether it's through portfolio standards, lots of different possible mechanisms. I'm going to talk about one specific one that's here today in the US for CCS code 45Q on the next slide. You need a workable regulatory and legal structure, especially for storing the CO2 in the ground. The EPA has, under their underground injection control program, something called Class 6 wells that they created for storing of CO2. There's some issues with that. People think that regulatory process needs to be revamped to really move forward. Other places in the world have very different regulatory structures. Here, it's private ownership of the pore space under our feet, but in countries, especially like Europe, the government owns that. So that's a whole different set of problems. We need infrastructure development, primarily for the storage and transport of CO2. In Norway, the government's funding major infrastructure development to develop storage sites in the North Sea. Canada put out money to put a pipeline in Alberta called the Alberta Trunk Line, which takes CO2 from some industrial sites to storage sites. The idea of what's called hubs, where you have industrial hubs that can sort of pool their CO2 together and then have a single transport storage system is taking place. And there's about a dozen of these hubs that are under discussion in different parts of the world. Then, of course, we're going to need public support. I won't say much about that, except that there's both good news and bad news. The CCS isn't visible enough to have a real vicious anti-support from the public, but this public also doesn't know about it. So it's sort of an open slate here, and it's very important as we move forward to educate people and show the positives of this. And finally, innovation. I think it's true of all technologies. And you can look at it being spurred by two ways. You can have technology push, which is really R&D programs. The Department of Energy has major R&D program in this country, but you also need market pull. In some ways, market pull is just as important, if not more so. And once you have the market pull, you get a lot of innovation, you get a lot of learning by doing. So the 45Q tax credits, these were originally started in 2008, and it will give, and there it gave $10 per ton for every CO2 used from anthropogenic sources for enhanced oil recovery. Enhanced oil recovery is where you put the CO2 in the ground and it helps get more oil out of a reservoir. And $20 for geologic storage. It was expanded in 2018 under the Bipartisan Budget Act. The values were raised to 35 and 50, and it's taken 2 years since that Budget Act's been passed. Just last month, the IRS just finalized the rules and they went in effect. Also, in December of last year, there was a 2-year extension for project start dates. The projects now have to start by January 1st, 2026 to get to qualify, and there's expectations that this date will be expanded in the future, just as the tax credits for renewables keep getting extended through the tax extender programs. This hasn't really developed any projects in the U.S. yet. There's a lot of them there's a lot of talk. We'll see now that the IRS rules are finalized what comes to fruition. But what's going to mainly happen here is going to be industries that have pretty pure CO2, which is cheap to capture, things like ethanol plants, maybe ammonia plants, and have fairly easy access to storage, things that are near infrastructure. It's a lot of pipelines in the oil patch in the US that have been developed for enhanced oil recovery. Those are the type of projects we'll mainly see coming out from this. But maybe in the future, they'll keep expanding the eligibility and the monies to get more projects in. So I'm going to just stop there and be happy to take questions.
Great, thank you. Does anybody have any questions for Dr. Herzog?
I have a question, Professor. What you mentioned that some of these projects, like the carbon capture and storage attached to a bioenergy plant, require these kinds of carbon credits, whether it's a tax credit or a payment or something on a market, in order to be viable. I'm wondering what levels of basically carbon prices are required to make that happen.
So, there's a variety of sources, and depending on what the exhaust gas looks like that you want to take the CO2 out of, the cost will vary. I say if you want to decarbonize the electricity system, the numbers are going to be in the order of $50 to $100 per ton of CO2. And so that's the range we're looking at there. Our early projects are going to cost more money because we don't have the supply chain, all the knowledge there. So your first movers cost more. But once you get past that, I think if you have things in the $50 to $100 ton range, you start seeing some projects going on. Yeah, but of course, if you're talking about things like negative emissions, our bioenergy and CCS, those need numbers more like $200 a ton, and direct air capture much more than that. I put that in the range of $600 to $1,000 a ton today, or today, probably through about 2030. So it's
That's
not
really helpful. I think the bill that we support in Congress has prices in that range for around 2030.
So one thing that's got people excited, the California Clean Fuel Standard, which is running about $200 a ton of CO2. So several people are trying to get that. Now to qualify for that, you have to do something like use the negative emissions, and so they'll use they'll get CO2 from the air. What one company's trying to do is get CO2 from the air and use it for enhanced oil recovery, then sell that oil to California, which would be very low carbon oil, and claim the money. But for the $200 a ton, plus you can add the an extra $50 or so for the 45Q. I don't think they can do it for 250. There's a company called Carbon Engineering, and they're in partnership with Occidental to do something in the Permian Basin. So they have an announcement out that they want to do 1 million ton per year plant, and that's what's driving them. But I think they're a little over optimistic on the costs they're going to achieve.
Any other questions? Gleb?
Hello, thank you for the presentation. I had a question. So is it only carbon capture, or what about other gases like methane, nitrogen? They're important too, right?
Well, yeah, that's not my area. Methane is more than, well, you can people do capture methane at things like landfills. And, actually that's what they call, I forget the word, green gas. It's, green gas, green bio, so biogas. So they do that, in terms of, there's a lot of methane leaks around. So what you want to try to do is clean up those leaks. That was one of the things that Trump did away with, some of the standards in the fracking industry for controlling methane. I think Biden canceled that already. Actually, a lot of the majors were unhappy because the majors were, doing pretty well in terms of it. It was a lot of the wildcatters that were pretty sloppy about that. But some of the methane, a lot of the methane comes from rice paddies, cows. So that's not so easy. And I really haven't heard much people, I'd call it capturing it from the atmosphere. Basically, methane is not nearly as long lived as CO2 in the atmosphere. So, you're talking about a couple of decades, and it will actually degrade to CO2 at times. So,
Gotcha.
and the other ones, N2O, once again, a lot of that comes out with the nitrogen fertilizers. I don't know much about it, but I think it'd be very hard to capture. But some of the things that come out from agriculture, like that methane and then the N2O, that you can counterbalance with negative emissions, and because they're very difficult to mitigate.
Anybody else?
I do have a question more on like the economics. So when you were describing certain amount of dollars per ton in your conversation with David, for example, was that what does that number, that dollar amount represent? Like, is that in tax credits, or how much it'll cost the company to remove and sequester the carbon?
You have to be very careful in the literature with dollars per ton of CO2. First of all, when I first started, was talking dollars per ton carbon. Now everybody pretty much talks dollars per ton of CO2. Of course, it is a factor of over 3 difference between those two. But so today, talk dollars per ton of CO2. But then, is it gross CO2 or net CO2? So is it the amount of CO2 you capture, the gross amount, or is it the net amount? Because a lot of times when you capture, whether it's from the atmosphere or from power plants, you have to use energy, and they emit CO2. So you really only can take credit for the net amount. So when I talk dollars per ton of CO2, I mean the net amount. And when you do that, it's pretty much the same number that you would have if you have a carbon price. So you have a carbon tax, that will be equivalent to that carbon tax. So, if it costs me $75 per ton of CO2 to do it at a power plant, but the carbon tax would be $100 per ton, it'd be to my economic benefit to do the capture, because it's less than paying the thing. Now, you got to be careful somewhat, because once again, it's like leasing or buying. There's risk when you put in all this capital equipment, because it may take 20 years to get all your money back. And so you gotta, if there's risk that things could happen that 20 years, if the savings isn't big enough, say that the tax is 80 and it's gonna cost you 75, well, that starts getting in the noise, and you may not go ahead with the project then.
Got it. Thank you. So the dollars per ton of CO2 is what the company would have to pay either in like a carbon tax or to sequester.
Right. Yeah. And a lot of times you'll see the term with the car in CCS, dollars per ton of CO2 avoided. That means that's the net amount. You don't want the gross amount captured, just the amount you avoid putting in the atmosphere.
I think one more question, and then we'll let you go. Gleb?
How small of a scale are we talking, or can we go? I understand, industry cluster, right? Bunch of factories kind of pulling their CO2 from smokestacks. Can we go to the like city level or neighborhood level? Can we go towards like a private house?
The economics don't favor that. I mean, technically you can, but realistically, it's hard. It's the big demonstration projects are on the order of 1 million tons of CO2 a year. So most of the big demonstrations are 1 to 5 million tons a year. They're smaller pilot projects they have out there, but unless there's like a CO2 pipeline almost next door, a lot of times they'll just release the CO2 in the atmosphere because it's too expensive to do something with. So really, this is a fairly big technology. Now, in some of the air capture plants, they're running pilots about 1,000 tons a year now. So those are fairly small. But once again, they're only running those when a lot of times they're piggybacking them on a storage operation where they add to something that's already there. Yeah, I don't foresee this going into households and people have looked at putting it on automobiles and that. I just don't think it's realistic. I think there's a lot of less expensive opportunities.
No
Well, thank
catalytic
you.
converter. Yeah.
Thank you for your time tonight. And I just want to let you know, again, thank you for also being an endorser of the Energy Innovation and Carbon Dividend Act. And we expect the bill to be reintroduced in the current Congress. And when it is, we'll be back in touch with you to let you know any of the updated details on it.
Okay, very good. Well, nice to meet everyone and have a good evening.
Thanks again for your time.
Bye-bye.
Bye.